Let's take a look at the next example where we have CH2O. Again, the number of valence electrons. Here we have 4. Here we have 1 times 2. And here we have 6. So 4 plus 2 will give me 6. 6 plus 6 will give me a total of 12 valence electrons. Now here we have 3 atoms. We have carbon, we have hydrogen, and we have oxygen. So you have to determine which of them is the central atom. Hydrogen is obviously out, but it cannot be a central atom. So we have between carbon and what? Carbon and oxygen. So let's come back to the periodic table over here. We have carbon here and we have oxygen. Remember I told you that electronegativity increases this way, which means that oxygen is more or less negative than carbon. And the central atom is the one that has the least electronegativity, which means that carbon will be my central atom. So the rest, which is oxygen, hydrogen, and other atoms there, will be terminals. So we have 2 hydrogen atoms, H, and we have 1 oxygen atom. We have 1 oxygen atom. Okay, so that's that. I told you earlier that every bond you see represents or contains 2 electrons. So there are 2 electrons here, 2 here, and 2 here. That's a total of 6 electrons. So removing 6 from 12, we'll be having a total of 6 remaining. Okay, so the next step says you should assign leftover electrons to the terminal atoms in order to complete that octet configuration, right? Okay, I'm not going to add to hydrogen because there's no way that rule, and I'm not going to add to this hydrogen. I'm going to add to this oxygen because oxygen only has 2 electrons here, but it needs to be 8. So I'll add electrons around it to complete its octet configuration. Okay, so let's go. I'll add a lone pair, a lone pair, a lone pair. Let's count the number of electrons we have now around oxygen. We have 1, 2, 3, 4, 5, 6, and 2 here. That's 8. So it has a stable configuration now. So how many electrons I add to this? I added 6. So remove 6 from this 6. We have 0. So we are done. But this is the structure. But if you look at this now, go back to my my rule 4. It said when you don't have any more electrons, you are usually done. Usually, that means sometimes it may not be done. You have to consider some things. Okay. Now, every atom I explained must have a stable octet, especially carbon must have a stable octet. Although some atoms I explained earlier, they don't obey that rule, which we're going to see some of them in very soon. Okay. So carbon here must have a stable octet. Let's calculate the amount of electrons that carbon have in this compound. Okay, let's see. It has 2 here. It has 2 here. It has 2 here. That's a total of 6. So it is not complete. It's not complete. So this cannot be the structure of CH2O because carbon here it does not have a stable octet. So what can we do? Okay, so in most cases, the central atom may not have an octet. In this case, we create what? Multiple bonds. We create multiple bonds. Let me circle that so you can see that as a reference. We create multiple bonds. So what can carbon do? Carbon can look for how to get another electron, okay, to form a new bond. You understand? To form a new bond. And the only atom here that is electron sufficient is this person, this atom, oxygen atom, has lone pairs of electrons. So carbon can take one of the lone pair of electrons in oxygen and use it to form another bond. Okay, so how's that going to be? Let's withdraw that. It's going to be something like this. We're going to have our C, our H over here, let me change the color to white, our oxygen. Our oxygen now has used all the lone pairs. Okay, so how many lone pairs does oxygen have now? It will have just 2 lone pairs left, and this lone pair was used to form another bond. Are you seeing that now? So this is the level structure of CH2. Let's see if it is correct. Look at oxygen here. Does it still have a stable octet after sharing its lone pair? Let's see. We have 1, 2, 3, 4, 5, 6, 7, 8. Wow, that's still stable. Let's see carbon. We have 1, 2, 3, 4, 5, 6, 7, 8. So as everybody's happy now. So this is the level structure of CH2O. Okay, let's take a look at Cn minus, Cn minus, okay, Cn minus. So here we have carbon, the usual traditional way. We have to find the number of valence electrons. So in carbon, we have 4 valence electrons. In nitrogen, we have 5 valence electrons. So if you add this up, this will give me a total of what? 9 valence electrons. So I told you here, I said subtract an electron for a positive charge, and add an electron for every negative charge. Because this is a negative charge, it means that it has gained an electron. Okay, a positive charge, a positive ion means that those electron, negative ion means that gain electrons. What do I do here? I will have to add one more electrons. That will give me a total of 10 valence electron. Okay, so here we're going to have we have 10 valence electrons. So we have to determine which of them is the central atom. Coming back to our table, our periodic table, we have carbon over here and we have nitrogen over here. So carbon has a lesser left negativity. So carbon is the central atom and nitrogen is the terminal atom. So here you can see I've used up, let me put this here. I've used up one bond and that one bond contains 2 electrons. Let's subtract from here. We're going to have 8 electrons remaining. So what do? We assign the valence electrons now to the terminal atom. Don't forget that nitrogen here is the terminal atom. In form of what? In form of lone pairs. So let's go that. So nitrogen now has a stable octet count 1, 2, 3, 4, 5, 6, 7, 8. Now I've used up 6 electrons. So what is left? 2 valence electrons. So since I have more, who will I give this remaining one to? I'll give it to the central atom. Okay, so let's give the central atom the 2 lone pairs. So remove 2 from this, we're going to have 0. So this should be the negative structure of Cn minus. Now, one more thing you have to do is that you have to add, okay, before that, take a look at this. Nitrogen here has 1, 2, 3, 4, 5, 6, 7, 8. That's a stable octet. Very good, nice. But look at carbon. Carbon has just 1, 2, and 2 here. That's 4. Does not have a stable octet. So what will carbon do? Carbon must have a stable octet. So as I said earlier in the other example up here, one of the low pairs of nitrogen can form a shared pair. So what does it become? It becomes something like this. We have our we'll change that. We have our C, our N, and we have, how many lone pairs will be left here? We have 2 lone pairs remaining, and we have a new bond that was formed from this lone pair. So nitrogen has given one of his lone pair. But if you look at this now, carbon now has 1, 2, 3, 4, 5, 6. It's not still complete. So again, carbon will go back to nitrogen again and take another lone pair, form another bond. So how does it look like now? It looks something like this. Now that carbon has, nitrogen has used one of the lone pairs, it's going to have 1 lone pair remaining. It has a bond initially from this and has a new bond here from this lone pair. So look at this now. Does carbon have a stable octet? Yes, it does. 1, 2, 3, 4, 5, 6, 7, 8. But does nitrogen have a stable octet? Yes, it does. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So because this is an ion, we have to put this in a square braces and add a negative charge. Okay, we have 2 more examples. We have, because of the screen is not white, so I have to write it down here. Xenon fluoride and PEEP and ALH3. So let's try xenon fluoride. Zn and ZeF2. Same method, same process. What we have to do is to calculate the number of valence electrons. Xenon is a noble gas. And as we know, all noble gases, they have a stable octet configuration. Which means that they have 8 electrons in the outermost shell. While fluorine here, and halogen has 7 times 2, because we have 2 here over here, so that's times 2. That will give me 14. 14 plus 8, that's a total of 22 valence electrons. So again, the central atom will be xenon or fluorine. Now, as I told you about electronegativity, it means the ability of electrons or atoms rather to gain electrons. Xenon has a stable configuration, so it does not have any business with electrons. So it does not want to gain electrons. That means it's going to have a lesser electronegativity compared to fluorine. So hence, xenon is my central atom, and fluorine, the 2 fluorine atoms are my terminal atom. So I've used up 4. 2 here, that's 4 electrons. Let's remove 4 electrons from this. Let me write it down here because of space. Remove 4 from this, you have a total of 18 valence electron remaining. Okay, So what do we do? We know already that we have to assign these valence electrons now to the terminal atoms in order to complete their octet configuration. So let's go. We have that, we have this. Okay, we have that, and this. So count it now. You can see that fluorine now, the two fluorine atoms now have a stable configuration. So this is, I've used up, I've counted the red dots. I've used up 6 here, 6 here. I've used up 6 plus 6, that's 12. I've used up 12. So 12 minus 18 will give me 6 valence electrons. So what do I do to the remaining 6? The rule says we should assign the remaining, if we have any other one remaining, you should assign it to the central atom. So I'll give that to the central atom. So 6 electrons, which means 3 lone pairs. So we have 1 lone pair of xenon, another lone pair of xenon, and the third lone pair. This is the leverage structure of XeF2. Lastly, we have AlH3. Al has 3 valence electrons and hydrogen has 1 valence electron and 3, because we have 3 atoms here. That will give me a total of 6 valence electrons. So let's see which of them is the central. Obviously, hydrogen can never be the center, so the central atom is aluminium. Okay, so we have 3 hydrogen atoms. We have hydrogen over here, we have hydrogen over here, and we have hydrogen over here. There are 3 hydrogen atoms here. Okay, now you know what we do now. We subtract the number of electrons. We have 2, 2, 3, that's 6. Subtract 6 from here. That will give me 0. Wow. So we don't have any electrons to assign to the central atom. If you look at this very well, you can see that hydrogen here does not have a stable. Aluminum here does not have a stable octet. That's just 6 electrons around it. 2, 2, 2, 6 around it. Which means aluminum, and there's no way we can do this, what we did up here in Cn minus, where we can take a lone pair and assign it, because there's no lone pair on the terminal atom. So that means that this is the structure. This is the leverage structure of AlH3. That means the aluminum here is an exemption of the octet true. You can have 6 electrons around it, so having 8 like others. Look at xenon as well. Look at xenon here. Xenon has, let's count. Let me shade it in gray. There are 2 electrons here. There are 2 electrons here. That's 4. We have 2 here. That's 6. We have 2 here. That's 8. We have 2 here. That's 10. So xenon also exceeds the 8th rule, the octet rule, that's having 8 electrons. So xenon also can also be an exemption to the octet rule. I advise you to try on this XeF5 plus. So pause this video and try to attempt this. Okay, I'm assuming you've attempted that now. So let's do this real quick. So xenon has 8 valence electrons. Fluorine has 7 times 5, that's 35. 35 plus 8 will give me 43 valence electrons. But because we have a plus charge, it means that as lose 1 electron, that will be a total of 42 valence electrons. Again, xenon should be my central atom. Let me bring this down. Xenon should be my central atom, so we should have fluorine, and fluorine. That's 5 fluorine atoms. Okay, so I've used up how many electrons in total? I've used up 1, 2, 3, 4, 5. That's 10 electrons in total. So let's subtract 10 from 42. We're going to have 32 valence electrons. Okay, so what we do now, we assign these 32 valence electrons to the terminal atoms, that's the fluorine atoms, in form of lone pairs. So let's go. We have that. Okay, now how many electrons have I used in total? I've used up I used 6 per fluorine, so 6 times 5, that will give me 30. So remove 30 from 32, we have 2. So according to these 2, we assign this one to the central atom. So let's just look for a place to put it, and let's just put it to be somewhere around here. Okay, so this is now actually the way the structure of the molecule. We'll talk about that later in later videos on VSEPR theory. Okay, so this is the level structure of XeF5 plus. And don't forget, you have to add this to show that it's an ion. You put a plus sign up here.